It's really common to represent time-varying signals in terms of their RMS levels. RMS stands for root mean squared, for reasons that I'll discuss later in this video. RMS levels are used in most fields where periodic signals are encountered. Examples include electricity and electronics, acoustics, and structural vibrations. RMS levels give us a simple way to compare different types of time-varying signals, such as square waves, sinusoids, or random noise. This comparison is based on the average power of the signals of interest. The RMS level of a time-varying signal corresponds to a DC, or constant value, that delivers the same average power to a resistor as the time-varying signal does. RMS values of signals are sometimes referred to as the effective value of the signal. First, let's derive the relationship that gives the RMS level of a time-varying current. The instantaneous power is the product of voltage and current, so the power dissipated by a resistor with some time-varying current is R times I squared of T. The average power is the integral of the instantaneous power over one period of the signal divided by the time period. Since the resistance is constant, I can pull that out of the integral, so the average power is R over capital T times the integral of the current squared with respect to time. The resistive power dissipated by a constant current, I effective, is just R times I EFF squared. Since I EFF is constant, the power is also constant, so this corresponds to an average power too. Our goal is to determine a value of the constant or effective current that results in the same average power dissipation as the time-varying current I of T. To do this, we equate this expression and this expression. The resistances cancel out, and we can solve for I effective by taking the square root of both sides. So the effective current is the square root of the mean value of the square of the time-varying signal. Now let's go through the same process for the resistive power dissipation resulting from a time-varying voltage. The instantaneous power is just the square of the voltage divided by the resistance. Calculating the average power as before results in this expression. The power dissipated by an effective constant voltage, VEFF, is just VEFF squared divided by R. If we equate this expression and this expression, we get this. The resistances cancel out again. If we take the square root of both sides, we get the result that V effective is the square root of 1 over the time period, T, times the integral of the square of the voltage over that time period. This is the form of the effective value of an arbitrary time-varying function f of t. It's the square root of the mean of the square of the function, which is referred to as the RMS or root mean square value of the function. This level is the constant value that provides the same average power as the original time-varying function. In this class, we'll only be concerned with sinusoidal signals with zero average value. For this particular case, there's a simple formula for determining the RMS values. The RMS value of a sinusoid with zero DC offset is just the maximum or peak value of the sinusoid divided by the square root of 2. Finally, you can use RMS voltage and current values in the average power formula for sinusoidal signals. If you do that, the average power is the RMS voltage times the RMS current times the cosine of the voltage phase minus the current phase. There's a lot of terminology associated with AC power. So far, we've defined instantaneous power, average power, and RMS values. In the next video, we'll introduce even more terms, mostly associated with the power of energy storage elements.